These are the forces that act upon the particle and they can control its movement towards its velocity. Sedimentation rate, you can say. This is also, you can also refer to it as sedimentation rate. At what rate it is going to be sedimented. Very important thing I am making you understand. I am explaining you this. That what are the factors that act upon the particle which is getting sedimented. Now we will talk about the Wedberg unit, S, that you might have seen. Ribosomal subunit. What do you write? 80S ribosome is comprised of 60S plus 40S. There are two large subunits, small subunits. In bacterial system, 70S ribosome. It is made up of actually 50S plus 30S. Why these two units are not additive? These two units are not additive. I mean 60 and 40 is 60 and 40 is 100, but you are writing 60 and 40 80. Mathematically it is not correct, no? Why it is like this? Because this Wedberg unit is not the mass. It is not the weight of the substance. It is the rate at which the bodies get sedimented. Okay, sedimentation rate. So you are a body having greater mass, having equal masses, two bodies having equal masses with different shape. Archimedes principle you must be knowing. If you change the shape of a nail, if you make it flat like a boat, it will not sink, isn't it? So shape is also important, not only mass, shape is also important. So when these two bodies fit together like this, they become compact. Okay. The shape that they attain, it cannot have the additive value of those. It depends how they fit together. And definitely ribosomal subunit have a specific way of fitting together. The larger subunit with the smaller subunit, they associate at a particular position. So that the mRNA that will pass through that particular region and the polypeptide will be synthesized and will come out. So it has a specific shape, specific, you can say, three-dimensional or quaternary conformation. So what is this S is? S, this is not exactly sedimentation coefficient. That is, we call S is Wedberg unit. S remaining silent, we call it Wedberg, not Wedberg. Tu buches? This is Wedberg unit. Actually, Wedberg, he was the person in 1920s who invented this particular ultracentrifugation technique. He developed ultracentrifugation. Centrifugation, ultracentrifugation. The simpler one we call centrifugation. That is used for differential centrifugation or differential separation purpose. The other one that is called ultra, a very high speed centrifugation technique. I was talking about that it is vacuumated because there is frictional force that is generated inside, which will hit the centrifuge tube and will damage the molecule that you are separating, trying to separate. That's why in ultracentrifuge, the machine is first vacuumated and it runs at very, very high speed within a liquid. Always there is a medium within which you are trying to separate that. And this Stoke's law works upon that particle. Every separating particle, settling particle, this formula, this particular theory will work upon. To simplify this, there is a term called sedimentation coefficient. Sedimentation coefficient. Also, you may represent it as S. Sedimentation coefficient is equal to V by omega square R. This is the formula for sedimentation coefficient. S is equal to V by omega square R. Your V is same, that velocity, the sedimentation rate. According to Stoke's law, you can replace this V with that right hand portion of that equation, Stoke's law equation. So to make it simple, you can, when you are talking about a particle sedimenting in a medium, you can directly go to this formula. You can skip that middle part. To make your answer a little bit simpler, যদি বুঝতে অসুবিধা স্টকস ল মনে রাখতে প্রবলেম হচ্ছে, then you can directly jump to this. এবারে একটা স্ট্যান্ডার্ড কন্ডিশন আছে। স্ট্যান্ডার্ড কন্ডিশন হচ্ছে যে সেডিমেন্টেশন কোএফিসিয়েন্টের একটা স্ট্যান্ডার্ড কন্ডিশন আছে, যেটাকে আমরা বলি S20W. S20W means at 20 degrees centigrade in water, the sedimentation coefficient is known as the standard sedimentation coefficient, and it ranges from something 1 into 10 to the power minus 13 to 10,000 into 10 to the power minus 13 seconds. This 1 into 10 to the power 13 seconds, this is equivalent to 1 S, Rydberg unit. That means these ribosomal particles, 80S or 70S, they have a sedimentation coefficient of 80 into 10 to the power minus 13 seconds, or 70 into 10 to the power minus 13 seconds, like this. Isn't it? Eta others sedimentation coefficient. It means wherever it is written, the S Rydberg unit is given, that is equivalent to this much. You just multiply that with 1 into 10 power minus 13 seconds sedimentation coefficient. Okay, that will give its original sedimentation coefficient. Koto sedimentation coefficient is settle down hoche. If somebody wants to calculate V, S is equal to V by omega square R, then he has to have the idea of, one can calculate omega from the revolution per minute, RPM, through RPM you can calculate omega, you have the R, you can calculate V, because you know the density of the medium, the density of the particle, the radius of the particle, these things you know, okay, you can measure measurable quantities. So you can finally measure the amount of V. So ultimately you can calculate the sedimentation coefficient. So these are the different principles in which all types of centrifuges work. So in the last class, minus 13. No, this is not minus. From this to this. Ranges from this to this. Sedimentation coefficient ranges from this to this. You follow this particular write-up. If you don't buy it, you can at least you can take a photograph of it. Now I talked about the types of centrifuges, types of different centrifuges on the basis of there were different bases. One was on the basis of the type of rotor, fixed angle rotor and swing rotor type, isn't it? Another is on the basis of its working principle. On the basis of its how do you apply it? On that basis, there are two types. One is that differential centrifugation. Another one is that should be called isopycnic, na? Rather, we should broadly call it density gradient centrifugation. And then we will divide that into two types. One is rate zonal density gradient centrifugation, another is isopycnic density gradient centrifugation. So on the basis of the application, centrifuges are of two types. On the basis of its application, centrifuge how you use it, centrifuges are of centrifuge or centrifugation rather are of two types. One is differential, centrifugation, another one is density gradient. This density gradient centrifugation can further be divided, classified into two types: rate zonal density gradient and another one is isopycnic density gradient. Or you can also say isopycnic or equilibrium density gradient. This is also called equilibrium density gradient. What are these things? We'll have an idea about that. Equilibrium density gradient centrifugation. Differential centrifugation, I already told you that this centrifugation, it runs at differential rates. You gradually increase the speed of the centrifuge so that the smaller and smaller molecules get separated out. Here is the diagram I was given in this book. This is cell homogenization, cell homogenate. That means the cells has been homogenized. It has been lysed using some lysis buffer, okay, and it has been crushed so that everything comes out. If it is an eukaryotic cell, as we mentioned, there are several cell organelles: nucleus, mitochondria, chloroplast, Golgi bodies, endoplasmic reticulum, ribosomes, lysosomes, microbodies, different things are there. So at the very beginning, most largest is the nucleus. In most cases, it will be the largest. There are exceptions where you will find that the mitochondria is as big as the nucleus. In case of some protozoa, it happens like that. The Kinetoplastida group, the kinetoplasts mean the mitochondria. They're very big. There is only one mitochondria inside. Some of the, kinetoplastids like Leishmania, it has only one mitochondria inside, and that is as big as is the nucleus. So if the two are similar in size, shape, etc., they will be different in density. It is not like that everything will be same. It is unexpected, very rare case. They will be different in density. They may be same in size. So their separation will become a little difficult. They will form bands very nearer to each other. Or you cannot separate them by this method. You have to go to isopycnic or rate zonal density gradient centrifugation. So here we are talking about differential centrifugation. This machine is comparatively simpler. It may be an ultracentrifuge where you are rotating at very high speed, okay, but the liquid that you have used, it is not density gradient. It has a uniform density all along. There is no gradient. Gradient means what? Either in increasing order or in a decreasing. It has a slope like this. That is, in mathematics, the slope is called gradient, isn't it? So here we mean gradient means it gradually increasing density in the tube. The liquid that you are using in the tube, centrifuge tube, will have an increasing density gradually. Okay, that is the case of the density gradient centrifugation. But here the density of the liquid is same all along. Only density of the particles are being different, their radius are being different, and on the basis of that sedimentation rate, Stoke's law, they're getting separated at different speeds, different RPMs. So at the first, you used 600 G to separate the nuclei. Nuclei get separated And the other and also some cell debris, means the cell membrane and other things, that will also come along with the nucleus. So if your work is with nucleus, maybe you are doing some, what is that is called, run-on assay. There is a kind of an experiment, run-on assay, in which we label the nucleotides, the RNA, inside the nucleus, and then we do an auto-rad. If it is a fluorescent molecule, we observe under the fluorescence microscope or confocal microscope, where are those molecules going? Under certain condition, you have treated the cell with maybe certain drug, or it is under stress or some problem has occurred. Under that situation, what is the expression profile of this cell? You can do a run-on assay for that. That is one thing, you need nucleus. In that case, your job is over. And if you need something else, maybe mitochondria, will go further. You will take the supernatant. What we usually do, when you at first run, you will get a pellet and a supernatant. Okay? So both these things have become separated. You can easily take the supernatant, so automatically the pellet will be left inside. If you want to use the pellet, you use it. You throw it out, the supernatant, you discard it, you don't need it. But your purpose is to purify maybe ribosome, maybe something else. So we'll go further. At 20,000 G, you are getting mitochondria, peroxisome, lysosomes together. And other things like endoplasmic reticulum, Golgi bodies. Probably it is an eukaryotic animal cell. That's why chloroplast has not been given. Otherwise, chloroplast might also come along with mitochondria if it is of same size, shape, etc. If it is of different shape, size, if it is larger, it will come before mitochondria. If it is smaller, it will come after mitochondria. After before means speed. Then, when you take the supernatant contains microsomes. Microsomes mean smaller vesicular particles that bud out or come out from the endoplasmic reticulum. So those are in the supernatant, they will get separated at about 1 lakh G. And in the next left supernatant, you will get the rest of the cytosol, means the liquid part of the cytoplasms, that is called cytosol. Here few steps have been shown. You might require further steps. It depends on the particular cell you are using. In my lab, we used to use, it was not exactly my work, my colleagues. My work was a little bit different. It was purely genetic engineering. But my fellow friends, they used to separate mitochondria from Leishmania. Leishmania donovani, from Leishmania. Leishmania, you remember, Kala-Jur, pathogen of that. And Leishmania has only one mitochondria that is equal to the size of the nucleus. That's what I was saying there. So separating it is a difficult task. You need to do this density gradient centrifugation. Okay. So density gradient centrifugation, now come to density gradient centrifugation. There are two types, as I mentioned, rate zonal density gradient, isopycnic density gradient. What are these? In rate zonal, there could be two types. Rate zonal density gradient. There are two types of way in which you make the density gradient. One is you layer the medium that you are trying to use. It may be sucrose, it may be phycol, like medium may be sucrose, medium may be phycol, like this. And there may be other media also. And you make different densities of these. Okay, you have different concentrations of sucrose, one higher concentration, one medium concentration, one lower concentration. In other words, one higher density, medium density, lower density. And you layer them one after another. So this is the higher density. First you pour the higher density one. Then you pour the medium density. solution. And you have to pour very carefully, otherwise they will mix up. Okay? They will mix up and you will totally destroy, spoil the experiment if you don't make this gradient properly. Then you pour the lighter density solution above that.